Hello everyone, and welcome to the first episode of our Chemistry Revamped series. This is a series in which I'll take concepts from chemistry and build it all from the ground up. So when we talk about science, there's usually three fields that come to mind. There's physics, chemistry, and biology. And of course, this course is going to be centered around chemistry. But in addition to that, we're also going to be bringing in physics, since physics is pretty much the field that really describes the underlying mechanisms of reality. So, in this lecture today, we're going to see how we can get from physics all the way to chemistry. So, that being said, the real question is, what are we going to learn in this video today? Well, let's put it this way. If any of you have ever played Minecraft, you know that you must have materials before you can craft things, right? So, in this video, it would be the equivalent of knowing what materials you can craft with. So, as any good scientist would do, let's first ask some questions. And that question would be, what is matter even made of? Well, back then in ancient Greece, someone by the name of Aristotle would probably answer that with, well, there are four elements. And those elements constitute all the things that you can see, touch, smell, or do pretty much anything with. Well, that's actually kind of inaccurate. So, actually, what's going on here? The thing here is that there is actually a less popular school of thought, a way of thinking, if you want to say it that way, and it's coined by Democritus. So, what he basically said was that, hey, all matter is composed of really, really small particles. Say, cheese particles are made of cheese particles. Well, yeah. Say, cheese is made of cheese particles. And he called those things atomos, which roughly translates to indivisible. So this was actually not that popular back then, so it was left on the shelf until a certain John Dalton picked it up and retconned the theory a little bit, years later. So, the retcon being, Dalton only said that only elements can have this smallest particle form. Other stuff like cheese or apples are just composed of these elemental balls. So, two scientists actually want to dig deeper into Dalton's theory. So, they set up an experiment where they try to discover the innards of that little sphere. And via the experiments, Thompson confirmed that there's actually negatively charged particles called an electron inside of all atoms, and Millikan just confirms their charge. And these particles are called electrons. After these discoveries, they proposed that the atom should actually look like plum pudding, where electrons are dispersed in the atom, coupled with some positive charge. However, their theory is just about to get retconned by some Ernest Rutherford. To really understand how stuff in the atom is placed, Rutherford set up an experiment where he sends an helium atom, without its electrons, well, better known as an alpha particle, into a gold sheet. And if the atom is exactly as those two propose, the alpha particle would actually just pass right through the atom. But not to anyone's surprise, really, that's not the case. There are some alpha particles that were actually deflected back. So, Rutherford made a conclusion that the atom must have a centralized nucleus in order to deflect the alpha particles backwards. And what he proposed is that the electrons actually orbit around the atom, much like satellites orbit around the Earth. Though most alpha particles would pass through inevitably because most of it is empty space. Though there is a catastrophic problem to this model, being that electrons actually circle around, when they circle around the atom like a satellite, they actually drop onto the atom in very, very short timescales, meaning that atoms would be inherently unstable. Well, that's actually not true, right? So the way to fix this is to essentially broaden the perspective of us on electrons. Electrons don't just behave like particles. They can also behave like waves. So why? Why do they behave like waves? Well, a certain Louis de Broglie guy would actually agree with you, like, why? Well, he states that particles can behave as waves, and vice versa. But, well, for those of you who want a more concrete example of why this is, well, actually you won't get the answer why it is, but you'll get a physical example of why it is, of how it occurs, rather. Look no further than the infamous double slit experiment. Yes, we just have to accept that particles in the subatomic world really behave differently from, say, like a paintball, or a few beads, or things like that. So let's take a look at the infamous double slit experiment here. So if we were to set up this right here, two walls, one of them has two small slits not far apart from each other. If we fire some solid paintballs into one of these holes, into the walls rather, and the balls would just pass through the holes, we would expect this pattern to happen. But, well, with waves, it's a little bit different. Waves are able to break formation into circles when passing through the hole. This phenomenon is called diffraction. And when you have two slits next to each other, the crests add with the crest, trough with trough, and it creates these lines, which in turn creates this pattern, which is the double slit experiment interference pattern. But surprisingly enough, electrons also create this pattern. So this basically confirms that electrons behave like waves. So de Broglie actually combined his idea with one Niels Bohr, and actually created a pretty solid model for how atoms work. Firstly, the electrons only orbit in discrete radii. They never hang out between orbits. Well, this is because if we describe electrons as waves, the number of nodes is always a whole number. Otherwise, the wave would not be able to sustain itself. If it's a whole number, then it would be able to sustain itself and continue to exist. However, if we have a radius that's not a whole number, and hence a non-whole number of nodes, the thing is that the electron waves would actually interfere out with itself and won't be able to sustain itself. So it would just interfere itself out and die out, eventually. Another feature of the Bohr atom is that the energies of these orbits are discrete as well, and only electrons can occupy certain energy levels. So, how do we actually allow the electrons to change orbits? And the answer is actually quite simple. We give it energy in the form of light, electromagnetic waves. But how would it actually jump? From level 1 to 2 or 1 to 3? I'm not sure about that, right? the way we actually control these transitions is by controlling the energy of light. Less energy, and we jump from 1 to 2. Increase the energy, and we jump to a higher level. So the way we control the light's energy is by actually adjusting the frequency. The higher the frequency, the more energy, and the lower the frequency, the less energy. That's why high frequency electromagnetic waves such as UV, X-rays, gamma rays, and whatnot are more dangerous than lower frequencies such as infrared or radio, since these waves can actually excite the electrons to an energy level that's so high that the electrons would actually escape the atom, making all sorts of mess. The problem with this is that the model, well, it's not solid yet, and it comes from this guy, Heisenberg. Oh wait, not that Heisenberg. The Heisenberg that he's named after. Walter White Heisenberg was actually named after Werner Heisenberg, the German physicist. And his theory goes like this. Essentially, if you have a particle with some location and some speed, and you really happen to know the speed exactly, well, the thing is that if you know the speed exactly, you don't know the position precisely at all. It can be literally anywhere, infinite possibilities. But if you so happen to know the position exactly, the particle would actually be traveling in all sorts of directions that you don't really know where it is. So there's a limit to how much we can actually measure two quantities at once. And the Bohr model is abolished and replaced by a certain cat lover's model, Erwin Shrödinger. So Schrödinger decided to take an alternate route and came up with a new type of wave, a wave function. So these wave functions describe a certain probability. You can kind of view these as some sort of probability waves propagating through probability medium or whatever you can come up with. And it also stores the particle's information. So if we square the wave function, the higher the location, the more likely you're going to find the particle. And the lower the location, the less likely. And if you define a region like this, the chance of finding that particle in that region will be the area under the curve. If we stretch out the region to the edges of the wave function, the chance of finding the particle in the region would definitely be 100%, since we're covering the whole wave function. So, wave functions can tell us essentially the shape of particle distribution, or as I would refer to it now as just shape. And the shape would actually be determining the energy of the system you're talking about. But before that, we gotta know how we can actually construct a wave function, because it won't just arise out of nowhere, right? And there's something called the Hamiltonian that helps us describe the wave function. It's essentially a mathematical tool that determines the energies of a system. So, in, say, like a hydrogen atom, we have three energies. There is the kinetic energy of the electron, or E linear. There's the attraction between the proton and the electron, the charge energy, and the electron rotates around the atom, meaning that it also has rotational energy. And we plug this information into the Schrödinger equation, which we would get the energy and the shape of the wave functions out of this equation. So the Schrödinger equation actually gives us exactly the same energies as the Bohr model. However, there's a little bit of caveats here and there. So let's take a look at the first energy level. The wave function describing the first energy level is called an s orbital. And here's the slice of the wave function in 2 dimensions. An orbital can store 2 electrons, and the reason for that is because of a property of electrons known as spin. Electrons can either have spin up or spin down. These can be viewed essentially as magnets, where the arrow points up to the North Pole and the end of the arrow is the South Pole. So if you try to put 2 North and South magnets together, they can kind of stick together, right? But if we have a third wheel, well, which they don't like, it would actually repel either way. So that's why orbitals can only store 2 electrons. Well, this is actually vastly simplified. You can actually read more about this in chemistry textbooks. So let's take a look at the second level here. The second level has a new family of orbitals called p orbitals, and these orbitals have slightly bigger radius because they can rotate a little bit faster. And of course, electrons fill up from the bottom orbitals up. However, there's a little bit of an issue when they're filling up on the second level. The thing is that electrons, well, they're negatively charged, right? So they repel each other, and hence the s orbital actually fills up first before the p orbitals, leading them to have a sub energy level higher than the s orbitals. So they fill up last compared to the s orbitals. And that's it for the atom. So now that we're done with atoms, let's go on to the molecules case. So let's take a look at the 1s orbital for the hydrogen atom. It has 1 electron, right? And when we put it next to another hydrogen atom, the wave functions can actually overlap and, say, interfere constructively and create a new type of orbital called a sigma orbital, or more specifically a sigma bonding orbital. It's made by essentially interfering the positive wave functions with another positive wave function, kind of like putting 2 crests and 2 crests together and 2 troughs and 2 troughs together. Or you can take another way. We can actually just use a crest and a trough and interfere it destructively in order to create a new type of orbital called an anti-bonding orbital. In this case, it's a sigma star anti-bonding orbital. Well, the star actually just denotes that it's an anti-bonding orbital. So, there's 2 possibilities here of the electrons occupying either orbital, since, you know, we're in quantum land here. Anything can really happen. So, let's take a look at what the electrons would actually do. Well, electrons, they're like most of us. They don't really mind having that much energy. They just want to release as much energy as possible and be as stable as it can. So, electrons end up occupying the lower bonding orbital. And that's why hydrogen is more stable when it's together. So let's take a look at hydrogen's older brother, helium. The thing is that yes, helium's electrons would occupy the 1 sigma orbital, but they would also occupy the 1 sigma star orbital, which ends up pulling the energy levels higher than what heliums actually exist in. So that's why helium actually doesn't form bonds. with each other, and that's why they're called noble gases, because they don't really like to share electrons. It's already filled. So let's take a look at a different type of orbital, the p orbital. So the p orbital can also create its own type of molecular orbital. And this is called the 2-pi bonding orbital. Or we can go the destructive case. And create an anti-bonding orbital, or a 2-pi star orbital. And another caveat here is that, well, p orbitals can also form sigma orbitals if they interfere psi-on. For example, this is a 2 sigma orbital. So the thing is that sigma orbitals are orbitals that are constructed from interfering things head-on, and pi orbitals are made from interfering things head-on. So it's kind of really suggestive that the molecules would actually have 90-degree or 180-degree angles, seeing how there's no curvy joints or whatever. So we might expect that this would actually be the shapes of the molecule. But that's actually not true. Then what is this then? So let's take a look at a new concept, and this concept is hybridization. The electrons, well, the thing is that when you try to bond atoms to atoms, the atoms actually have electrons in their orbitals, right? So they kind of really don't like each other already, since the outside is mostly negative, shielding the positive, of course. So what the orbitals inside of the central atom does is that they interfere themselves with their own orbitals. For example, this here, they try to add the 2s orbital with 3 2p orbitals to create an sp3 orbital, which gives shape to the methane atom, which gives the shape of the methane molecule. We can also combine only just 2 2p orbitals to create an sp2 orbital. And the faded orbitals are just the orbital that wasn't really included in the hybridization, since there's a little protruding bond up there. So that's why benzene has its shape, 2D flat shape. And lastly, let's take a look at the 1-to-1 case, 1s orbital to 1p orbital, and we get an sp orbital. And this sp orbital gives rise to triple bonds. So beyond all of Schrödinger equation, there's actually something beyond that. Okay, let's start that over again. So that's it for the Schrödinger equation part. Unsurprisingly, there's something beyond the Schrödinger equation. And that something, well, that's called density functional theory. So instead of the wave function, the DFT actually uses a new type of quantity to play around with, and that's the electron density. The reason why that we have to switch electron density is because the more electrons inside of the atom, the more unpredictable it becomes. Since electrons, well, they can be in any position and have any sort of force repelling each other, and we don't really have that much of an idea for that. So that's why we swapped to electron density. So we may have a little bit of a better grasp on how electrons behave, even though it's still very approximate. So we plug some density into the Kohn-Sham equation, which is the central equation for DFT, and what we get out of it is the energies, forces, and momentum, which essentially help us have the ability to predict, well, essentially about any sort of chemical reaction. Well, what we learned here also has plenty of applications. For example, glowing. this is the glowing mechanism inside of a glowing mushroom. The molecule gains energy from chemical reactions, and they can release that energy in the form of light via an enzyme named luciferase. And talking about light and plant-like things, even though mushroom are fungi, plants actually really use this quantum ability to the maximum level. So this is basically the engine that drives photosynthesis, and as you can see here, light is the main component that will help us excite electrons in order to give plants the energy they need. And not to mention, pretty much all of electronics is based on quantum mechanics. Transistors, LEDs, yeah, those are all based on how electrons absorb and release energy. So the bottom line of this entire lecture, if you don't really have that much to take away from this lecture today, I'd like to give you just a tiny bit of quote that I came up with myself. As you can see, there's plenty of retcons and theories and developments and so much so on. The thing is that it's basically saying that, well, anyone can be wrong, so long as, well, we as the human race actually come together and fix the problem together, so that we may advance as a race. Thank you so much for listening. Whoops.